Thought I'd give you an opportunity to see what a sample for this weekend's homework might look like. On the side, we're looking to find if we can find final velocities if given acceleration, clock readings, and starting velocities. So for this sample problem, I'm going to use values that came out of first hour's wheel and axle data. And we said that we're going to assume that the wheel and axle accelerated at 0.6 centimeters per second, and we're going to allow that to accelerate for 20 seconds, and we're going to assume that it started from rest. So the initial velocity would be 0 centimeters per second, and from that we want to find the final velocity. Now, you're not required to show a graph of what this would look like for the homework. I thought it might be helpful to see what that would look like on a graph. So because the initial velocity was 0, we know the y-intercept is 0, and because it's a positive constant acceleration, we would have a positive constant slope. Now, we don't know what the final velocity would be, but we do know that for this problem, the final clock reading, I guess it's there, would be 20 seconds. All right? And we happen to know that the slope of the graph is 0.6 centimeters per second squared, or per second. So how do you do the problem? For each of these problems, you must start with writing down the original value, with the general equation. Final velocity equals acceleration times the clock reading plus the velocity at time 0. Then you want to fill in the original values with units. For instance, we know that the acceleration is 0.6 centimeters per second, or you can write it per second squared, times the clock reading. We said we'd let this run for 20 seconds. Now, the initial velocity in this case happens to be 0, so we actually don't need to include the velocity at time 0 for this problem. If you did, you want to add that in there. Next up, we just do simple math. We do 0.6 times 20, which you could use a calculator. If you don't have a calculator, you could think, well, what would 0.6 times 2 be? And that would be 1.2, so times 10 more would be 12. Now the units here, we have centimeter per second times seconds. So one of these seconds will negate one of these, leaving us with 12 centimeters per second, which would be the velocity at the 20-second mark. On side 2, we're taking a look at the relationship between position and clock readings. So in this time, we're using the values that came from the fake wheel and axle data that we did a week or two ago. And again, let's take a look and see what our position versus time squared graph would look like for this case. Well, we find a positive acceleration. We've got a clock reading of 4 seconds is what we're going to include here, which would end up being 16 seconds squared on here. But this one has a starting position of 15 centimeters. So we're going to have a positive y-intercept over here, and then we'd have a positive constant slope. Because the change in time is 4 seconds, we'd have to square that. So this clock reading here would be 16 seconds. Well, I guess I could put 16 seconds squared. We'll put the 16 here, and as we've done for other things, we'll put the units down here, seconds squared. This is, I guess, in centimeters. So how do we calculate this? First, you start with the general equation. Final position is equal to 1/2 the rate of acceleration times the clock reading squared plus the position when time equals 0, or the y-intercept. Well, for this case, we know that 1/2 the acceleration in this case is 10 centimeters per second squared, or centimeters per second, times the clock reading squared. So we have 4 seconds, but that is squared, plus the starting position of 15 centimeters, which goes there. So according to order of operations, we have to take care of these exponents first. So again, we'll say final position is equal to 14 seconds squared is 16 seconds, but it's 4 seconds times 4 seconds. 4 times 4 is 16. Seconds times seconds is seconds squared. Notice that that's on the inside of the fraction. You could also do a manipulation of this of 1/2 times 10. We're going to run all those calculations at the same time because these represent real things from our lab, plus the 15 centimeters. So 1/2 of 10 is 5. 5 times 16 would be 80. And the units for this are centimeters per second squared times second squared, so the second squared cancels out, which gives us 80 centimeters plus 15 centimeters. So it looks like in this case our final position is going to be 95 centimeters. So in review, it's important for each one of these that you start with the general equation. I guess I wanted to make that a star. Start with the general equation, fill in original values with units. If necessary, do some calculations and make sure you have a final answer that includes what you're calculating along with the values and units. I hope that helps.